Alright, we have been discussing for the suspend animation problem not in the previous part. Then next we can propose some potential solution can address this problem for the GCM model. So I hope you still remember in the previous part we illustrated when we learn a very deep GM model with multiple layers, then the model may suffer from a suspend animation problem not if we have a deep architecture of more than 5 layers on the core dataset. No matter how many data or how many epochs we train the models for these deeper GCM models, they will not be responding to the training data anymore. No matter how many epochs we are training them, right? And they will be suffering from the suspend animation problem not for deeper GCM models, as shown here, right? Then how can we address this problem? Then next I'd like to propose another model proposed by my group, and we try to incorporate the residual learning into the GM model architectures. I hope you still remember what is the residual learning. Originally, we use the residual learning for building a deeper CEM models, by creating some connection or highway connection among layers. And in here, we try to incorporate this residual learning into GM models as well. Besides conventional residual learning, we also extend the residual learning into some new forms by considering graph structures instead. In this page, we show with different GResNet architectures, the graph residual network. So on the left-hand side, we show you the vanilla GCM model. Given the graph structure together with the raw feature for all the nodes, we can fit them into the SGC layers. Now with 2 layers of SGC layers, we can learn the embedding vectors for all the nodes, and we also classify them into different classes, like Y-hat as shown here. So this is a vanilla GCM model. And generally, if we have a GCM model with 2 layers, then we can achieve very good performance for the node classification task as we studied before, right? We would mention if we have a deeper GCM model with multiple SGC layers on top of each other like this one, then we'll be suffering from the suspend animation problem or not, because we cannot train them anymore. Then how can we address this problem? We can potentially address this problem by adding the residual learning into the GCM model, the deeper GCM model. In this page, we show you one of the potential architecture we can build for the GResNet with a naive residual learning. Naive residual learning, we use the raw or conventional residual learning, creating the highway among the layers. For example, given the graph structure together with the raw feature vector of all the nodes, we can fit them into the SGC layer as shown here. So besides the SGC layer, we also create one highway to forwarding this kind of raw inputs, the X inputs into the next layer as well to be summed with the output by the SGC layer, the first SGC layer we show here. And then we can further feed the summation between the raw inputs together with the output by the first SGC layer into the next layer as well. And we also create some highways connection between the second layer to the third layer as well as shown here, right, and so forth. So this highway denoting we will have one copy of the inputs to be summed to the output result instead, right? So by adding multiple highway connection among layers, we can build a very deeper GCM model, with naive residual learning. And we can illustrate the performance of the naive residual learning, in the next page. So in this page, we show you with the GResNet model performance, combined with naive residual learning, to build a deep model architecture. So according to the plots we show here, we show both the training accuracy together with the testing accuracy of the GCM model. It will show you the GResNet with 1 layer until 7 layer. And we also show you with the training accuracy as well as the testing accuracy with regard to the training epochs we provide in the datasets. So according to the plot, we see that this naive residual learning can potentially address this problem, right? Because we see that the plots, even for the model GCM model with a 7 layer, we can still be able to learn them with the training curve as shown like this one, right? Similar for the testing curve as shown here. So compared with the original suspend animation problem shown here, the training curve is much better actually. We will still be able to learn a deeper GCM model and achieve very decent performance for deep architectures. At the same time, we also see that for the deeper GCM model compared with the Shannon models as shown with 2 layers, their performance is still very bad, which is approaching 0.4 as a testing accuracy as shown here, right? In other words, this naive residual learning cannot totally address the problem at all. One of the potential reasons can be because of the graph structure. Because we may need to incorporate the neighborhood information together in learn the embedding vectors, right? If we only incorporate those raw features in the next layer by the higher weights, we may potentially lose some potential information among the neighbors, right? Therefore, we may propose another potential solution and try to extend the naive residual learning terms with this graph naive residual learning instead. What does this mean? So here we define the copy we incorporate for the layers, via the highway for each layer to be added to the next layers. Here instead we try to incorporate this graph structure into define the residual terms, for the highways. In other words, the term we add into the next layer will be times with a head matrix. And this head defines the normalized adjacent matrix of the graph actually. In other words, if we have an input, we times one with this a head and to be summed to the next layer. Similar for here, we will times one with a head to be summed to the next layer as well, and so forth. Therefore, we can define a new term to be added for the reading learning as is a head times the hk minus 1 to be summed to the next layer, right, and so forth. So by incorporating the graph structure, we also illustrate the performance for the GResNet, with different layers as shown in this page. So compared with the previous one, purely based on the average reading learning terms, so by incorporating the graph structure, we can potentially, address the problem or not, right? In other words, so for the models with deep lead, we can achieve better performance than the naive one, right? Because the curves is much higher than the previous one we illustrate here, right? So incorporating the graph structure seems to be a very promising direction for defining the reading learning terms. However, we see that their performance is still lower than the two-layer model architecture as we show here, right? We may wonder what are the reasons. So we further define some new terms by incorporating the raw features as to define the reading learning terms to be added to all the layers, in the deeper GCM model. And we also further incorporate the graph raw feature as well. For the raw reading learning term, we got all the x into each layer as we show here, right? Which is different from the naive term. So for the naive one, we add all the embedded vector as by the highway to the next layer. However, for the raw reading learning we show here, we add this x as reading learning terms to be by the highway to each layer instead. Based on this raw reading learning, we also incorporate this graph structure into define the highway connections among the layers. So we can define one more reading learning term, which is called graph raw reading learning. We define the highway as this a head x as this term to be added to each layers in this deeper GResNet architecture. We can also show you with the performance for both this raw and graph raw reading learning terms in the following plots. So by adding these raw features into each layer for reading learning, we show you the performance of the models with deep architecture in this part. So we find that for the training curves as well as testing curves, if we add in these raw features into each layer, then their training curve will be much better if we have deep architecture. At the same time, we also find some of the downsides if we add in these raw features into each layer. For some of the shallow models, their testing accuracy will be lower down slightly. Now for 2 layers and 1 layer that we show here, right? And this problem can be addressed by further considering the graph structure by using this graph raw reading learning terms instead. So by adding a head x into each layer as avoid highways, we show you the performance of the learning plots in this page. We'll find that the learning curve is much better than the previous ones. For the shallow model architecture with 2 layers, we can still learn very good performance in both training and testing as we show here, right? So by creating some highway among the layers, we can potentially address the suspend animation problem mentioned before for learning the deeper GCM models. And this technique will be extensively used in the following part for creating the graphbert model as well for learning deep architectures.